Okay, so when we left off, we were having a family reunion, confined in some kind of a small little house, spilling rain outside. The house becomes unstable, and somebody has to go. So, of course, your grandmother checks out the room and decides Uncle Harold is the one that's unstable. So she fires Uncle Harold out, and then she waits to see if the house becomes stable, if the energy will decrease enough that things will be stable again. If it does, then we're done. If it doesn't, then she might look around and think, oh, Aunt Gertrude has to go too, and chucks Gertrude out, and then waits. Now, could be that she might decide Aunt Gertrude and her two kids need to go, and would throw them out as a unit. So lots of times in radioactivity, nuclear radioactivity, what's really happening is it could be one particle being chucked out, or it could be a combination of a couple of protons. And remember, we talked about Rutherford's alpha particle. We found the alpha particle in nuclear reactions. It was the first subatomic particle that we discovered that was getting fired out of a nucleus. And it's two protons and two neutrons. But they're not thrown out separately. They're thrown out together as one unit, as an alpha particle. So that would be like Aunt Gertrude and her two kids being thrown out. Anyway, a nucleus will continue to throw out subatomic particles from its nucleus until it reaches a stable state. That might happen with just one emission, or it might take 3 or 4 emissions before it reaches a stable state. Lots of times, depending on what it's emitting, by the time it's done, it's no longer the element that it was. It has totally changed. Okay? So this whole process of throwing things out, it's spontaneous for the most part. There's tons of elements in our world that are spontaneously nuclear reactive. Okay, they undergo what's called radioactivity or radioactive decay. They're naturally radioactive, meaning they just do it on their own. When they're formed, they weren't stable, and so they're emitting particles. Now, sometimes we create things that are naturally not naturally, but once we've created them, they're radioactive. Okay, but for right now, we're going to look at the ones that are radioactive without us messing around with them. Okay, so a nucleus, if it's unstable, it may emit subatomic particles spontaneously. So we haven't touched it, it's doing it on its own, and it's going to keep emitting things until it becomes stable. So the original nucleus is naturally radioactive, and the process is called natural radioactivity or radioactive decay. The rate at how often that it tosses out a subatomic particle to become stable is called the rate of disintegration. Okay? And this rate, how quickly it tosses something out, can't be changed no matter what you do to the element. It's not like a chemical reaction where if you heat it up, or if you stir it, if you do some kind of physical change to it, it'll speed up the chemical reaction. Heating it up, stirring it, dropping it, doesn't change the rate of disintegration. And that rate of disintegration, if we hop down, you would have talked about in math already. Okay, it's called the half-life. Before we go there, though, just a couple of little notes. I already said earlier, every element has at least one radioactive isotope, but it's the next point that's kind of neat. All isotopes of all elements with an atomic number greater than 83 are radioactive. 83 is kind of like that key number that once you get 83 protons inside the nucleus, no matter how many neutrons you have in there, that's going to be unstable. Okay, and if you think of it, if the atom's the size of the room, you get 83 positively charged particles that don't like each other inside the tip of a pin, then it's going to be unstable. Oh, by the way, the atom isn't the size of the room, so the nucleus is significantly smaller than the tip of this pin. Definitely going to be unstable. So bismuth is 83. Anything above bismuth, Every time, no matter what isotope it is going to be radioactive. And I already mentioned earlier that it's the 3,1H for hydrogen that's radioactive. All right, so half-life. I know you've looked at them in math. I don't know if you've looked at the physics part of it, but at least the math part in the sense of how do you calculate it. But the half-life is really exactly what the name implies. Whoops. The name implies that it's the time it takes for half of the sample to become stable. So no matter how big the sample is, the amount of time it takes for half the atoms inside the sample to become stable is called the half-life. And so after the first half-life, one half will be stable, one half won't. After another half-life, half of the half that was left will be stable, and then again half, and it just keeps going. In reality, you will never get to then the whole sample being stable. There'll always be some little piece that will be left because of the half. Sorry, I was just changing my sitting position. Didn't mean to move the camera on you. Okay, and so if you think, if you start off with 60 grams, after one half-life you would have 30 left, after second half-life 15, then 7.5, and then 3.75, and you would just keep going, but you'd always have something left. So the equation we tend to use looks like this. And I'm using m's for right now, where m is the mass of the mf is the mass that's left over, mi is the initial mass, and 2 to the n. The n is the number of half-lives that have passed. So if 1 has passed, then you just divide the initial sample by 2. If 2 half-lives have passed, you divide the initial sample by 4, etc. Now, these masses don't always have to be masses. They could be the number of atoms. They could be, so it could be capital N, or it could be the count. Sometimes in the question it'll say that it has this count. So whatever it is, whether it's the number of atoms that are going to decay, whether it's the mass, whether, it's the same equation. You can just change it from M to N or to C. Okay? Now this 2 to the N. So the N is the number of half-lives. And we can get the number of half-lives if we know that have passed, if we know the total time, and we divide the time by t 1/2. That's the symbol for half-life. And I don't think I wrote this piece down anywhere in your notes because it's kind of common sense, right? If a half-life is 4 days and 16 days have passed, how many half-lives? Hopefully 4. The half-life is 3 days and 27 days have passed, then it would be 9 half-lives. Okay, so to figure out the number of half-lives that have passed, take the total time, divide it by the time for one half-life, get the number for n, and then it's 2 to the n that you divide by. Okay, each isotope of each element will have its own half-life. So even though it's the same element, it doesn't mean it'll have does not mean the two isotopes will have the same half-life. In your textbook, there is a chart of half-lives over here on page 621, and so you'll see the half-life of hydrogen, carbon 12. That's the radioactive isotope of carbon. Iodine. But as you go down the table, you'll see there's several different half-lives for uranium because there's different isotopes there. Okay? So for the rest of the class, I'd like you to do some half-life questions. So on page, and I think it's on the back side of your sheet. If I could just turn the sheet over. There it is. It's up at the top. So page 621 is where the chart is, and then if you would do the questions on page 622, 9 to 12, and let me look and see if I really want you to go all the way to 17. I'll let the teacher know that because I have 6 seconds left before the video runs out. Okay, thanks.